All right, welcome. Here we are starting our chapter on matrices. A matrix, that's the singular form of matrices. A matrix is basically just like a box of numbers. You can see on my calculator here, I've got a couple of boxes of numbers. It has a 6 and a 7 and a 7 and an 8 and an 8 and a 9 and a 9. Those are just matrices. It just looks like an array of numbers, kind of a little grid of numbers. And our calculators do this well, although it's kind of clunky, a little bit inefficient. I just wanted to show you some things that you can do with your calculator today. Your matrix button is found just below the math button on your calculator. You have to push second matrix to get there. You can see that I already have some matrices entered for B and C, and I'll show you how to do that a little bit later. If you go second quit, that's my favorite way of getting it back out to the main screen. But I've done some math with my matrix B and C. I've added two matrices together. I've doubled the matrix. I've taken B minus C. I tried to multiply B times C, but it gave me an error. So more on that later. I wanted to talk about this RC idea. Have you ever heard of RC Cola? I'm not even sure it's a thing anymore. It's kind of like a Shasta sort of thing, but it's the way I remember how to think about matrices. Matrices have a thing called dimension to them. So when you look at matrices, they have a certain number of rows, like this one has 1, 2, 3, 4 rows, and it has 1, 2 columns. And so we call it a 4 by 2 matrix. And so I remember that we always put the first number as the number of rows, and the second number is the number of columns by thinking of RC Cola. So we always describe the dimensions of a matrix by its rows and then its columns. We'll talk more about that as we go. So I am starting with 8.2 and then going back to 8.1. It just makes more sense to me that way. So again, we are talking about dimension of a matrix being its rows times its columns, rows by columns. Here I have just sort of a general matrix with they call each of those A values an entry. This top left entry is called A11 because it's in the first row, first column. And so if you look at this one, it's got 12 numbers in that matrix. It looks like it's got 1, 2, 3 rows and 1, 2, 3, 4 columns. Would that be a 4 by 3 or a 3 by 4? Remember, we do rows then columns, so that would be a 3 by 4 matrix with 12 entries in it. Again, we are going to talk about adding, subtracting, a scalar multiplication, all of those much faster to do without a calculator. Also today we're going to learn how to do matrix multiplication. You have to understand how that works, but those can be quicker to use a calculator, so you'll have to know how to do it both ways. And today we'll learn how to set up a matrix equation too. So let's start with addition. So can you see if we take this 2 by 3 matrix plus this 2 by 3 matrix, and it's just as easy as you might think. We are just going to add the corresponding entries. So we'll add A11 to A11 and get our new A11. And just component-wise, like you would add vectors together almost, right? You'll be able to add vectors add matrices really easy. And subtraction works the same way. Here we've got a 3 by 1 minus a 3 by 1 matrix. And if we subtract matrices, it's going to work the same way. Trust me when I say it would take a lot longer to enter these matrices into your calculator and make your calculator do this work for you. Here we've got a 3 by 3 matrix plus a 2 by 3 matrix. Now this is a little more confusing, right? Because if we match up this one with this one, and this one with what goes with the 6? Well, we would say that this one has a dimension mismatch. This one's not possible to add together. So we say that you can only add or subtract matrices of the same dimension. Here we've got one that's a scalar multiplication. Works just like scalar multiplication of a vector. If you start out with a 3 by 2 matrix, you'll end with a 3 by 2 matrix, and each little entry will just be multiplied by -2. Pretty simple. Matrix multiplication, a little more complicated. And the first thing that makes it complicated is that you saw the error on my calculator. It's actually not always possible. And so let's see what makes it possible. This one looks to be a 2 by 3 times a 3 by 3. We know we couldn't add those or subtract those, but we can multiply those. Here's what makes them multipliable. If these inner two dimensions are the same, if the columns from this matches the rows from your second one, they will be multipliable. And then what you want to think about is, how big is my answer going to be? My answer is going to be these other two numbers. My answer will be a 2 by 3 matrix. So that's how I usually start, is by setting up how big of an answer I'm looking for. I know I'm going to be getting 6 numbers out of this. So I'm going to find the product of those two numbers. It's a little complicated, might remind you of a dot product. Here's how it goes. So in the same vein as RC Cola, we're basically going to take the rows from the first one times the columns from the second one. And what I mean by that, remember I mentioned the dot product, is you're going to take the 0 times the 1, plus the 5 times the 1, plus the -3 times the 11. Maybe I'll write that out this first time. 0 times 1, plus 5 times 1, plus -3 times 11. And if you want to use little post-it notes to help yourself cover up the numbers that you don't need to be looking at the time, that can be helpful too. What do we have? 0 plus 5 plus -33, I think is -28. That only gives you one entry. It gives you the first row, first column entry of the product. You might have guessed, to get the next row, we're going to move over. And so the next row, I'll be taking the 0 times the -4, the 5 times the 2, the -3 times the -6, and adding all of those together. That one comes out to 0 plus 10 plus 18, and that one's positive 28. Repeating the process, we're still on that top row. Now we're in the third column. That's going to get me my top row, third column entry of my product. That'd be the 0 times the 0, the 5 times the 2, and the -3 times the 9. 0 plus 10 plus -27, -17. We're done with 3 out of the 6 entries in our answer. So we're going to switch to the bottom row and repeat the process. Bottom row, first column, bottom row, second column, bottom row, third column. So you can see it's kind of a process, which is the reason that the calculator can be useful. It probably will save you time to use the calculator. So I'm going to show you how to do that, but I want you to understand how we could get each entry, and I will hold you responsible for being able to show me that at least a few times. So we know to get this entry, we would take what? The 6 times the 1 plus the -1 times the 1 plus the 0 times the 11. Let's see if we can make our calculator do this for us though. All right, grab your calculator. You're going to start by pushing second matrix. Let's enter that 2 by 3 matrix as our matrix A. So these are just the names of the matrix when we start to do math with them. When we're entering matrices, we'll want to go over to the edit. So you'll want to go over, and you'll want to edit matrix A. Matrix A for us is going to be a 2 by 3 matrix. And it works best if you enter the rows first. So you go 0, enter, 5, enter, -3, enter, 6, enter. So there, I think I've got matrix A entered incorrectly. Now I'll want to enter that next matrix. Maybe I'll enter that one as matrix B. So I'll go to second matrix. Again, edit. We're going to call this second matrix matrix B. I'm going to overwrite this original matrix B I had in here and call it a 3 by 3 this time. And I'll just expand that and give me enough room to enter all of those in. I like to double check to make sure everything's looking good. Again, my favorite way to get out to the main screen is a second quit. And when you're ready, we're going to try doing an A times a B. So to call up A and B, we're going to go again to second matrix and now just use the names of them. So we're going to grab name A, just hit enter on there. It'll show up as A times second matrix. We'll use the second option for matrix B. And there we're getting some answers. Let's see if that matches what we killed it on that top one, right? So the bottom should wind up to be 5, negative 26, negative 2. Very nice. And then let's just look at what happens when we do the reverse, the B times the A. Using our post-it notes, we'd want to take, remember, rows times columns. So we'll want the columns on this one and the rows on this one. Yeah? Rows times columns. Can you see why we're getting a mismatch here? If I take the 1 times the 0 and the negative 4 times the 6, there's nothing left to multiply that 0 by. That's the whole thing about this dimension thing and why I was getting an error on my original multiplication problem. Here I'm trying to take a 3 by 3 matrix times a 2 by 3 matrix. Remember what I told you? You have to check those inner two dimensions, and if they don't match, that means you're not going to be able to get a product. That's when we're going to get an error. So there would be no product possible for these two matrices, which is interesting because every other place that we've ever seen multiplication, weren't we able to switch the order on multiplication? A times B should be equal to B times A, not in matrix land. The properties of matrix multiplication, there is the associative property, there is the distributive property. There's an associative property even when you're using scalars, but there is no commutative property. I wanted to show you one of these really special matrices. It might remind you of the triangle of opportunity. It's called the identity matrix. You're going to be amazed. So when we take our rows times our columns here, first of all, I've got, what dimensions do I have here? I've got a 2 by 3 times a 3 by 3. Are these multipliable? They are, because our inner dimensions match. And our answer will be how big? The outer dimensions are 2 by 3. So I can set up a 2 by 3 matrix as my answer. I should get 6 numbers as my final answer. And we're going to take rows times columns. The more zeros that are in these matrices, the easier the multiplication is, let's be honest. Because if I take 0 times 1, I get 0. 5 times 0, I get 0. 3 times 0, I get 0. Add those all up and it's 0. Nice. Moving over. If I take 0 times 0, nothing. 5 times 1 is 5, but then another 0, so that's just going to be a 5 for that column. Last column, 0, 0, 5, 0. Negative 3 times 1 is negative 3. So everything was a 0 except for that negative 3. What do you notice about my top row? Same as my original top row. Do you think the same thing will happen on the bottom row? Well, the only thing that happens in this first one is the 6 gets multiplied by a 1. Everybody else gets a 0. So if the 6 gets multiplied by a 1, there we have it. Moving to the next column. Everybody gets a 0 except for the middle one gets multiplied by a 1. That'll turn out to a negative 1. And then our last column, when we do matchy match, matchy match, those all 0 out except for this 0 times 1. But actually that zeroes out too, so we still get a 0 there. And what do you notice? we got exactly the same matrix as we started with. And so whenever you multiply something and it doesn't change at all, that's why they call this the identity matrix, because it didn't change it at all. It would also work if you put the identity matrix in the front. And in this case, they had to use a smaller identity matrix. It just has that diagonal of ones down the center. Here's a 2 by 2 times a 2 by 3. Are those multipliable? Matchy match, yes. How big of an answer should I get? Another 2 by 3. All right. And what do you suppose I'm going to get? Well, I'm supposed to get, if I have an identity matrix times some random matrix, I'm supposed to get that same matrix back again. It's like taking any regular number times 1. You just get that same number back again. This row times this column, this row times this column, this row times this column. All we're going to wind up with is those top numbers. And finally, we've got matrix equations. I just wanted to show you just how to set this up today. We solved these in the last chapter, but in this chapter, we can use matrices to solve. Let me show you how this works. So what we're going to do first is we're going to make a 3 by 3 matrix that'll just be the coefficients of the variables. Just the coefficients of the variables, which is kind of nice because now you don't have to write those z's every time. People are getting mad at me about those z's. Okay, and then we're going to put the variables x, y, and z in their own matrix. And we're going to put an equal sign. Well, here's the thing. I've got a 3 by 3 matrix times a 3 by 1 matrix. I know they are multipliable, and our answer should be how big? A 3 by 1. So my answer should be a 3 by 1. True? Well, when I take that first row times that only column, I should get 2 times x plus, let me write that down, 2 times x plus 4 times y plus 3 times z. Do you see how that's literally the top equation? And I know my goal is to have that equal 8. So I'm going to have an 8 be that first entry. Brilliant, yeah? And so the 8 and the 0 and the -7 wind up going over here. So for today, I just want you to understand how to set up a matrix equation. I would just be looking for you to write this out. Later, we'll talk about how we can actually get this matrix by itself. Maybe it's division, maybe it's using an inverse operation, right? But we'll be able to solve for the x, y, z in the future. For today, just setting them up.